So I'm the one between you and the coffee break, so I hope I will try to do this very efficiently. It was very nice hearing while I was off. It's really very nice to see this like generative AI taking over everything, probably taking over humans in the near future. I don't know. I highly doubt that. But you have to watch for the hallucinations of GPT. So sometimes they could overcome things. Anyway, thank you, Ermal, Jan, and then Katie here for the organizing this and for inviting me to this event. I really appreciate that. Today, I'm going to talk to you. I'm going to tell you about our journey in which we try to go to start with quantum convolution towards the efficient multidimensional convolutional classification. My name is Esam El-Araby. I am the lead of the KU ARC or Quark group at University of Kansas. And today, this is the outline of my talk. This work has won the Best Poster Award at QCUF last August. So I'll start by telling you the motivation for this problem, mainly about the convolution first, and then we'll see how we moved it to the multidimensional quantum classification. And then I'll tell you about some other application that we are using, we're trying to work on in our group, basically the PDE solvers, and then some wafer scale engine-based simulations and genetic environment-based compilation. Convolution, everybody knows what convolution is. It's nothing but just a sliding window on the data, and then some multiplication, some kernel that does multiplication and addition, back operation, multiply and accumulate, many different applications. However, in quantum realm, it's used in quantum neural networks. That's mainly the usage that is being heavily used in. However, in quantum implementations, there are some limitations and some things that we're trying to address with our implementation. The convolutional kernel in the quantum solution that we have here, they are fixed. The kernels are fixed. I'm not going to think of it as hardwired. They are single featured. And also they have very stride size, or like the moving window just jumps around and misses some of the data sets. Basically, it doesn't exploit the data locality very efficient.
Single feature, you mean it's black and white with RGB? That's that?
Yeah.
Okay.
And it also works at low dimensional, only 1D, 2D max. Here, we're trying to scale it up to any number, arbitrary, any number of dimensions, okay? So exploiting or preserving the locality of the data, the spatial locality as well as the temporal locality is very important thing for convolutional classification. And sometimes, usually they are very deep circuits, very like slow, very violate the coherence limitation. So the contribution here, very quickly, in the convolution kernel that we developed, it's multidimensional, arbitrary filtering rather than being fixed. Unity stride. It might sound very trivial, but unity stride turns out to be the most challenging one and producing the deepest circuits possible. So we try to optimize that as well. Multi-featured, all done in parallel, and we try to optimize it. We used Qiskit for that, and then the fidelity for like correction, like validating the correction, we achieved 100% fidelity in noise-free simulations. In doing that, we leverage some techniques, especially in encoding. There are a number of them. I'm sure all of you know that. Angle encoding, basis encoding, and amplitude encoding. Among these famous three ones, we have amplitude encoding, which is the most efficient in terms of the number of qubits required to represent the data, as well as the depths of the circuit used to represent the data. In our group, we developed an algorithm to do this, what we call C to Q, or classical to quantum, transferring, this is basically nothing but arbitrary state synthesis, state preparation. We call it C to Q, classical to quantum, and we published that a couple of years ago. We have proven that in that paper that we achieve like up to 25% to 50% improvement in circuit depths as well as gate count better than what IBM Qiskit does, right? So we're leveraging this technique here in some of the steps in the convolution, classifier, and I will talk about that later on. Another thing that we leverage also is the quantum shift operation, in which we need to generate these kind of shifted versions of the data, right? We use the so-called quantum incrementers, quantum decrementers, right? And basically, these are very essential. And then we optimize the circuit for that such that it's really very low depths, right? And then this picture shows here the incremental circuit and decremental. As you can see, they are the inverse of each other's. Then we use our convolution, the decrementers, not the incrementals. Related work in classical convolution, they are usually implemented using direct implementation, sometimes leveraging fast Fourier transform or GEM, general matrix multiplication. And the complexity and the best complexity among all these algorithms classically is O of n, where n is the size of the data. If you consider the size of the filter as another parameter, it's like NF, which is the size of the filter multiplied by the size of the data. That's a classical implementation. For quantum convolution, the existing work, they are fixed window, fixed filters. They use FRQI, NEQR, which are the other encoding techniques, spaces, and angle, which is not that very efficient, leading to very deep circuits, as well as large number of qubits required, right? Some of them use amplitude encoding. However, they are not generalizable to multi-dimensions. And also, sometimes the dimension, the distinction between the qubits, which ones represent which dimension, sometimes is not distinguishable, and that inhibits the degree of parallelism that we could exploit from the algorithm itself. All right. So our methodology in doing that. So I will show you this in like 3 steps. First, we need to generate the shifted or the replicas of data, shifted replicas of the data using the decrementers. Basically, you take the data. Mostly here we're using images, high-res images to do that. So you take that image and you produce multiple replicas of that image. Basically, each one of them is nothing but a shifted version of the original one. And then you could process those all in parallel, right? The second step is to do the second step of convolution, which is multiply, accumulate, just like the regular multiply and accumulate using the filters. And then we're leveraging our technique of CTQ, classical to quantum, but we need the inverse of it, not the direct, like unitary of them. All right.
When you're shifting the data, are you cutting off parts of it, or is the full data still available?
The whole data is still available. It's nothing but a rotation. It's not really like a shift.
Classical ML is the same to deal with knowledge or to deal with whatever about
If you have a huge, large amount of data,
yeah,
and the filter size is very small, you wouldn't care about those boundary conditions, whether they are lost or not. Okay. Yeah. So it's an avoidable problem in image processing, or like in this data, the boundary, we call it the boundary problem, the boundary.
It's a small effect.
Exactly. So you have to understand that, okay, these points, if you will look at this animation here, you see these boundary points, the white ones, are always problematic. And there are a lot of different techniques in image processing about linear extrapolation or replication or wrapping around, different techniques to deal with these boundary points. But to minimize the effect of these boundary points, make your data as large as possible, and the filter is relatively very small, that will not be a big problem. All right, so that's the MAC operation. And then we have to do, once we do this, the data is scrambled all over the place. We have to do some rearrangements to put the data all together into contiguous places so that we could build up the original image back so that it could be visually recognizable. So I will show you here an animation of our algorithm, only the simple version, which is the 1D, and then we'll see how we replicate that, or like how we extend that to the general version. So you start with this psi, this number of qubits, with the curly bracket here showing psi. That's your original data. We're not showing how you prepare those qubits. That's a preliminary step in processing. Okay, so these are the qubits necessary for the data. But in order to do that, the convolution this way, we have to add some more qubits to accommodate for the size of the filter. We call it the kernel. All right. That many qubits needed for depending on the size of the filter, the window of the filter, how many, in this case, how many pixels it is. Then if you have window of, let's say, four pixels, then you need two qubits. All right. And then after that, you put these extra qubits into superposition, and then you do the decrement. That generates the replicas of the images, as many replicas as you need. Okay. All right. And then here we're not using just the u of minus k. We have optimized u to the minus k into like a hierarchical pyramidal version of them, such that we only use u minus 1 in different qubits, not all of them. So if you, the direct inference is that u minus k with different k on all the qubits, but here we have this pyramidal hierarchical pyramidal structure of the u minus 1 only. That optimizes the depth of the circuit in a very good manner. And then after that, you apply the filter. And then if you have multiple features, you could add as many qubits as you have in features. That will be log to the number of features that you need to add. It's not linear, it's sublinear to the number of features. Okay. And then that's the filter. And then the data is scrambled all over the place. You need to organize them or rearrange them using the permutations of like the swap gates. All right. And then we have proved that, okay, this will work. But we need to, if you extend this to multidimensional, then these filters will be scattered all over. They will be distributed versions of the filters. So probably it will be, we proved it to ourselves, and swapping, like putting these positions before, swapping the swap gates with the filter in this kind of arrangements, put the filter only on those qubits, responding to the number of qubits, extra qubits, and the data is now available here. And we could now extend it to the multi-dimension much easier, and it would be more scalable in this sense to this one. All right. So now this is the multi-dimensional convolution that we have here. It's nothing but just now we have, with that kind of arrangement of the circuit, multi-dimensional convolution is nothing but just stacking one dimension in this way. You're just stacking the one-dimensional circuits here, and then this one now combined is the multi-dimensional filter, all in one contiguous circuit, right? Rather than being distributed. And that's the benefit of removing the rearranging first and then filtering instead of filtering and then rearranging. Okay. And then with that, we could do everything in parallel. You could do the convolution kernels all in parallel, the multi-featured and striding, and in all dimensions also in parallel, right? And the complexity of this, it's almost exponential. It's logarithmic in terms of the number of data versus, I mean, at least theoretically, like exponential, it's logarithmic in terms of the data size compared to the big O of n of the data size. It's O of log n versus O of n. Okay. And then this is like a complexity study that we did, comparing ours to the classical, to the direct classical on CPUs, the classical on using FFT on GPUs and CPUs, as well as the gem one compared to ours here in the left-hand side. Let me see if I have the laser here. Yes, this is our proposal here. The small n's represent the number of qubits you need. The big n's represent the number of data. Basically, big N is equals to 2 to the small n, right? So as you can see, it's logarithmic versus linear in terms of the complexity and classical. We did this. Now we try to expand to do it. The setup, we used Qiskit. We used also experiments on the actual hardware using IBM Costco, but IBM retired it. So we had a problem with that. So we had to move to another hardware. And the results were consistent. And then we used some simulations and we were the madness. And then we used the classical as a reference point to our results. And the filters we use different filters, averaging, Gaussian, solid edge detection Laplacian with different sizes, 3 by 3, 5 by 5 for 2D images. And then we did some pre-processing and post-processing steps with the padding of the zeros to make sure that data is in good, like a size, power of 2, if you will. And then the wrapping was used at the boundaries. That's your question. We did the wrapping for the boundary points. And the images, we used our mascot of KU, which we love so much. So the JHawk, from black and white images to RGB, ranging from 8 by 8 pixels to 5 by 5 by 3 bands, red, green, blue. However, this could apply to any number of bands. And then the filter sizes were 3 by 3, 5 by 5. For this, we needed 6 to 20 qubits for the data, in addition to the 4 to 6 qubits extra for the filters. The results for 1D, we started from 1D using this European Broadcasting Union, and then we used different sample size. We listened to it was consistently good, applying the filters classically and compare them even, and the quantum results, compare them even like audio and hearing them on like speakers. And then we moved to the 2D using our JHawk. This one shows us 128 by 128 black and white and then RGB. And as you can see here, in this image, you can see now this is the noisy simulation. This is the classical statistical noise effect. Okay, basically we're doing 1 million shots at minimum. Some other experiments we used even much larger number of shots. Different filters, different sizes, and then noise-free versus noisy, and then another filter Gaussian versus this the averaging, similar. And then this is the Sobel X. This is the Sobel Y, consistent with the noise-free. The noise-free we confirmed or we verified the 100% fidelity. It's exactly producing the same results like the classical version of it. And that's why we use the noise-free as our reference point. And then the Laplacian is the same image sizes, different sizes of filters. And then we move to 3D. We use the Kennedy Space Center data set. It's called Kennedy Space PSC data set. It's a data set of images that are like 128 by 128 by 128 bands. You could think of the 128 different like color components. Okay. So this is, what's that?
How many qubits of that one paper?
So 128, do I have anything here? Yeah, 128, let's calculate the number of qubits needed for this. 7 plus 7 plus 7, that's 14, 21 qubits.
Okay.
Yeah.
Will you later talk about the circuit depth and the number of entangling gates? Okay, those.
Yeah, I will be showing something. All right. So this is a 3D, what's called the hypercube or hyperspectral images. We used that from NASA archives. And then when we compare the fidelities, simulation-wise, 1D or 3D on the x-axis is the data size in terms of the number of pixels. That's basically the log to this number is nothing but the number of qubits, and then the fidelity. And this confirms or seconds what Tom was talking about yesterday. As you increase the number of data size for the fixed number of shots, 1 million shots here, you see a decline in the fidelity. That's typical. So this is trying to relate to what Tom mentioned yesterday. And then here, this is a 2D convolution, same story for different filters in different sizes, right? For black and white and RGB images as well. And when we move to the hardware, we saw the same thing, but it got a little bit like sketchy and then a little bit. I will show you some images. Hopefully, you will not laugh at them, but you will see how the hardware does. So here again, the effect of statistical noise as you go from smaller number of shots to larger number of shots. If you start with this image, use noise-free as your baseline, and then this is 10 million shots. You can see the artifacts and the people are Jayhawk here. This is the effect of this is like as if it's noise introduced in that image. When you increase the number of shots to 50 million shots, you have less errors. When you go to 100 million shots, it gets better. When you go to 500 million shots, that's this. So I know 500 million shots, it's a lot for you guys. But I know that the IBM was screaming at, we did this with Oak Ridge. So IBM was screaming at Oak Ridge. Oak Ridge came screaming at us. You guys have to be easy on the machines and then the job that you're submit. He said, okay, fine. I told my students, just take it easy. Just you proved your point. Just let's move on, right? However, when we take it now to the hardware, let's see the story in the hardware. So this is a black and white or RGB image. So noise-free, your baseline, and then 10 million shots noisy simulations. And then this is how it looks from the hardware. That's again what Tom was talking about yesterday, right? This is how useful quantum hardware is at this point in time.
You don't do any integration or anything like that.
We tried that when we're trying to use that, but didn't do much. All right. So that's a message. I said it right in the face. I said it in a private meeting with Jay Gambetta. They need to do a better job in their chips. Yes, we could do, yeah. So this image tells us two things that we need to do. Either to do a better job in terms of depth-wise, optimizing our algorithms. Yes, we're doing our best to do that. We're doing really, everybody here is doing a great job in doing that. But the vendors need to do a better job in making this technology really very good, useful. Yeah.
Well, I think what we need to be slightly more fair versus the vendors. If they tell us that the entangling gate fidelity is 3 nines, and the circuit has 10,000 such gates, we know that the result will be garbage, right? There's no need to run anything.
That's exactly my philosophy. Okay, the numbers looks good. The numbers look good. I could give you so many different numbers that shows I am doing a great job, but this is reality. And then I would let Tom probably even help me answering that question, right? From your, so we're in sync, me and Tom, in this. I am a computer architect by background. I need, when we started talking to the DOE at the beginning of this whole revolution of quantum, we were looking for another alternative for classical machines. We should never forget that we're nothing but building another machine. Quantum simulation is a good problem, okay, as Richard Feynman suggested, but it stayed there for quite some time. The interest wasn't there until Shor wrote his algorithm and everybody started feeling the threat. Then that's when everything started. So we need to use this machine. So we wanted to do things much faster and we needed to build this machine to do much faster things and in a much secure way and in a hopefully less budgeted money.
You tried other
Have we got it right?
other hardware other than superconducting?
No, when I talk to those people, we tell them, okay, guys, give us access. We have a big hammer, and then they scare away. We're trying to do it with IonQ. We're happy to do with Quantinuum. I'm happy. My student here, Kiran, suggested, when should we use Quera? So maybe with your help, guys here at Berkeley could help us get access to Quera.
Can you clarify what the depth of your circuit is that you're trying to run here?
I will show you some numbers.
Because I think this is the crux.
At some depth, it's not even worth running. Like, you should know.
Yeah, I know.
Based on the depth.
I know. I understand. As I said, we have to do two things. We have to optimize on depth. That's our responsibility. I'm not saying this is a shallow circuit. This is a very deep circuit. I understand. We're violating the coherence time. I understand that. But even with the smallest ones, I will show you that hardware is useless.
It's like trying to run CFD simulations on Abacus, right? Like you would not. You have to be realistic about what you can do.
We have some project going on right now on CF, on solving PDEs, and we're trying to use CFD for them. And then
It
for,
won't work either, I can guarantee you. It's not worth running.
well, we have something that is really good in which we're using Biscuit, and Biscuit is giving us a really a hell of a very good help there. It's not that, I don't remember, to be honest with you.
If you're trying to run anything more than, 100 entangling gates, on any device, I can guarantee any device, don't bother.
That tells, what is now the message? To whom this message should go?
To everybody.
No, to the vendors.
The vendors know it,
Not-
correct?
The vendors.
If they're telling you otherwise, then don't work with
Because
that vendor.
their device is stuck into coherence. They cohere very quickly. Right? As I always say to my students, even in the summer camps that I give to like high schoolers, these are schizophrenic cats. Schizophrenic sleepy cats. They sleep very quickly. Their coherence time is they sleep very quickly, and they're schizophrenic.
I think that's speak close to the mic for the people. Yeah.
I'm used to the interactive kind of mode in my classes. I'm sorry about that for the audience.
Which noise model did you use? Question online.
What's that?
Which noise model did you use? What model you're asking online?
This is the actual hardware.
Not for the noise duration.
For the noisy one, these are just the statistical noise. Did not use any noise model.
Okay.
Just seeing the effect of the statistical noise. Right? We didn't bother with using the so-called fake hardware that IBM. I hate the word fake they use, but let's go for the actual hardware. And then from our experiments, the actual hardware with the fake model are very consistently equal. So their fake model of their hardware is trustworthy. So I don't bother even what kind of noise model they have. I'm just using it, and then let's see how useful it is. So this is for averaging. Sobel, the same story. Laplacian, the same story. Gaussian, the same story. And then this is the table here. So this is it.
Okay.
So look at this. So the number of shots is in millions for different sizes, and so like the circuit depth. This is the circuit depth. That's the question that you're programming here. So this is the circuit depth, and the coherence time is just like 70 something microsecond. And then our calculations based on the circuit depths, and so we're very consistently close to what we actually measured. And then look at how the queuing time. My student stayed really waiting for a month for this. Yeah.
I think you need here one more column, total number of CNOT count, because this is now what is dominating, not the circuit depth, the number of CNOTs itself. This is how, at least when I run, this is now the best estimate how bad it will be. I just take the fidelity of one CNOT, take it to the power of number of CNOTs, and this is the result. So if you have 15 qubits and you are running now this highly parallel, so probably you have order of magnitude more CNOTs than your depth. So if you have 300,000 CNOTs, then the results is.
Why is the CNOT? I don't see why the CNOT would be more important. This is, by the way, this is the circuit depth and what is being reported by the tool itself.
By what?
By the tool itself from Kiskin. From Kiskin. I mean, circuit depth in terms of like levels of.
Circuit depth is one measure, and the number of CNOTs in the circuit is another measure.
Yeah.
From
No,
my
but what's the purpose of the number of the gate? The gate count, yes, it's a measure of how many gates you're using,
my intuition.
but how parallel they are.
I'm answering the question. So in general, each time you call CNOT, you make a small mistake.
Yeah.
So if you have 100,000 CNOTs, you have made 100,000 small mistakes.
Oh, you mean the error? It affects the error.
Yes, if every mistakes give you a little bit off, at the end, your total error, at least this is a bound.
Yeah. Okay.
So I just want to clarify what he's saying. Basically, what he's saying is that the error rate of the 2 qubit gates is much higher than the 1 qubit. So the circuit depth, we found the same thing in our benchmarks, right? That we have to focus on the number of 2 qubit gates is the larger factor for number,
We had that somewhere, but I don't have it here in my slides. Probably I will show you. Circuit depth, as far as I remember from here, is reported by the tool, is the level of all the gates, including the CNOTs and not the CNOTs.
So-
Yeah.
What would help you if you add total number of CNOTs as a column, and then CNOT fidelity to the power of numbers as another number. If this number goes to zero, you don't get the result. I mean, you'll be pure random.
That's true. My other way of calculating this is, okay, that's the circuit depth. We have delta T multiplied by the number of the depths. We estimate the execution time, and we convert to the measure, then it becomes the same, almost the same, right? Anyway, so Erman is about to kick me out while I'm still haven't reached half of my presentation. Okay, so let me move on really quick. That's the same story in the other hardware here, IBM Brisbane. And then when we move to now, this is just what convolution. Now we took it to the classification problem, and this is what we did. And by the way, this one also won in supercomputing last year.
Yeah.
Last year in supercomputing, was the finalist for the best research poster in supercomputing. And then this is how we built the classification based on the convolution, multiple different layers of convolution followed by pooling. And in pooling, we used quantum half transform or quantum wavelet transform. That's for dimension reduction. This is like when I asked that question. Quantum wavelet transform could be used for dimension reduction as well, and this is an example for it. Pooling is nothing but that. So the beauty of quantum half transform is basically it separates the data. It tells you which qubits you need to focus on among all of these number of qubits. Basically, it segregates the data into something called low frequencies versus high frequencies, and then all you need to focus on these low frequencies, which could be represented by a smaller number of qubits. That's why it's used in dimension reduction. And then you could think of this as a low resolution of your original data, but it's still useful resolution to recognize the data. And then for the connected layer, we use different flavors. I will move on. We have an optimized version of it, the full thing. And then we used real data sets, MNIST, Fashion MNIST, and CIFAR 10. Okay. And then as you can see from these curves, in terms of accuracy, we are lower accuracy than the classical ones because of the pooling techniques. We are using max pooling versus here we're using average pooling. But among all the quantum techniques were the best, all right, accuracy-wise. And same thing here for a larger number of larger size of images. And then this is the log loss ratio. And then here, this is now telling you how many parameters. This big bar here is the classical. That's how many parameters that you need to train your circuit on versus that small number of parameters that we are using here. That takes pretty much less time in training. Gate count. Okay, here that's what you're looking for. Yeah, gate count. We're almost the best among them here. Circuit depths, as reported, we are close to some of the. This is done with Oak Ridge, and this is it. And then PDE solver. We're trying to do. We have a technique that is really very good technique in which we're using two flavors or two variants. Called the variant one using Biscuit. Okay, and that's where we're using Biscuit. Biscuit is proved to be really very good for us. But compared to Qiskit, which and the second variant is based on Qiskit. Biscuit to Qiskit, they are both very good compilers and very good synthesizers. However, there are like advantages and disadvantages. Ed promised us that they will have an improvement in the next version. So Biscuit didn't scale well up to 8 qubits for us, but it produced the most efficient circuit depth-wise. Qiskit could scale up, but it wasn't a very efficient circuit. So I had another suggestion from Ed and some other person. I'm not here. I'm not sure if he's here today. Why don't you just like use Qiskit to produce the circuit and then use Biscuit to that's a good suggestion. I will try it. No promise that I will give that to Ed. And these are the results. So we used Poisson equations for that. 1D Poisson equation, 2D Poisson equation, 3D. So you could think, as you could see, the multidimensional kind of group. 1D, 2D, And then you can see here, this is VQE results, the wiggly line. And this curve is our solution, which is very close to the analytical one. And then this image here, 2D was, well, this is VQE solution. Totally, and this is the reference, the baseline, classic. As you can see, VQ is useless. And then it takes very long time, doesn't scale very well. This is our variant 1 based on biscuit. This is our variant 2 based on Qiskit. All right, same thing same story here when you go to 3D.
Discretizing the equations there.
What's that?
Are you discretizing the equations that are you including?
Are you using what?
Are you discretizing the equations that we did? Are you you have derivatives, right? Are you not derivatives?
Yes.
Yeah. So now that's the PDA story. As a proof of concept, I'm sure, I hope all of you know what WSE wavelet scale engine from Cerebrus. This is the company that produced the largest chip ever produced in history. Okay, we're using that to build a quantum simulator to prove to, like, we're bringing quantum simulations to their case studies, and then
That time memory.
yes, yeah. So and we're using that, and hopefully we'll get access to their latest hardware soon. So we did that, building a very basic quantum simulator, and on that one, we're meeting with them in supercomputing next week or so. And by the way, this PDE also got like the best poster finals for supercomputing, which we will present next. I'm sorry, I forgot it.
So how do you encode the discretized Laplacian in your problem?
So we discretize. There are some pre-processing steps and post-processing steps. So we do pre-processing by discretizing the PDE, and then use SVD and then polar decomposition to formulate the problem as a linear equation problem, and then take it from there. Basically, to generate the unitary from
So
there.
in your results, you said you're using the VQE. So are you mean VQLS? Like, are you solving the linear system or?
So after we give the same results, and then we try to generate the circuit for the VQ. Right. We'll take it offline for more details. So let's move on. And the last thing is genetic algorithms. We're using genetic algorithms for circuit synthesis and compilation. We're trying to compete with Biscuit. Hopefully it will be better, but I don't know. We have to talk us and Ed later on. And this is a student who's doing his work. This work hasn't been published yet. So, and with that, the acknowledge goes to all these guys in my group. They're doing an amazing job. Without them, I couldn't do anything. And then we'll end my talk with this announcement. I am editing a journal, which is a quantum-centric HPC, and its deadline is December 31st. I invite all of you, if you want to submit something, just talk to me. We could waive the fees, very $2,600 or so maybe. Okay, so tell me if you are interested, and that's the deadline. We are very happy to receive that. And these are the references, and then I know I stopped you from the break. Any more questions? All right. Thank you so much.
Yeah, thank you again.